Thank you very much. Yeah, thank you very much for the introduction. And I see all of you very small, but I really wish I could be there. I remember the last time I was there, it was an amazing visit, and I'm looking forward to the next time. And okay, so I'm going to do something a little bit not traditional in this talk, which is I'm going to start with a conjecture, and later I will show how this conjecture relates to the theorems I'm going to be explaining in the talk. And the reason I want to do this is because I think this conjecture came out from the application that we're going to see later. But I think it's it's kind of it's quite amazing that nobody asked this before. And I think it would be interesting even if it weren't for the applications that I'm going to show you later. So I'm starting with a question, and then it's gonna look out of the blue, not related to anything. But right after that, we're going to prove theorems to see what this is good for. So the conjecture is about reversing the isoperimetric inequality. So so if you have a subset K over N, then its isoperimetric quotient, this is just notation, is IQ of K is just its surface area divided normalized, so make it scale invariant, divided by the correct power of its volume. And so the isoperimetric theorem says that IQ of K is always at least, well, it's always at least what we care about. We won't care about constants, it's at least root n, but it's at least the IQ of the Euclidean ball, the standard Euclidean ball. So, but we don't care about the leading constant. We care, but it's just going to be relevant for the purpose of what I'm going to be discussing next. So the thing to remember is that there's always a lower bound of root of n for the isoperimetric quotient of every convex set, every measurable set in Rn. Now, a question which is an old question led to some very, very major developments that I will mention in a second, is just as overall is, can we reverse this? Reverse this. And the answer, of course, is a completely silly hope. There's no way to, starting from a set to bound from above its surface area, if you only know its volume, can be a union of arbitrarily many small balls. So you need some assumption. The obvious assumption is convex. So from now on, let's suppose that K is a convex body. And let's also assume that it's origin symmetric. So that means x, if x is in K, x is in K if and only if minus x, if and only if minus x is in K. The symmetry is not important for what the theorems I'm going to show next, but later we're going to be applying it to study the geometry, clustering questions and norms, and K will be the unit ball of the norm. So I just, from now on, whenever I write a K, just assume it's an origin symmetric. And then if you have a convex body in Rn, can you reverse the isoperimetric inequality for it? And again, the answer is obviously not. You can take in the plane a very, very long and narrow rectangle, right? And so that its height is, let's say, epsilon, and its length is 1 over epsilon, and you get volume 1, but arbitrarily large perimeter. So there's no way to bound the perimeter from above. But here we see that the issue, this is already an example of that the issue was that we chose the volume form on Rn, or the basis of Rn, incorrectly. And a very, very beautiful theorem and extremely influential theorem of Keith Ball, so it's called, called Ball's reverse isoperimetric theorem. It's from around 1990, maybe 1990, 1991, 1992, I don't remember exactly. So it says that if you choose the basis of Rn correctly, or choose what you mean by volume, then you can reverse isoperimetric inequality. So it says for any subset K over N is above, so convex and symmetric, there exists a linear transformation, let's say volume preserving, such that the IQ, the isoperimetric coefficient of S of K, is bounded from above by a constant multiple of n, but it's 2n, which is the IQ of just the hypercube, 2n faces. Okay, so in this picture here, if you choose your basis in such a way that these are the two directions, then it becomes a fat square, and indeed you bounded it by 4, and this is the plane. Okay, so but the point is that it is always true that any convex body in Rn, you can choose the basis of or change up to a change of basis. Its isoperimetric quotient can be bounded from above by n, and this is sharp. You have to think for 3 seconds, maybe a little bit more, why this is sharp. You have to prove that for the cube itself, you cannot do any better. You cannot find a linear transformation which makes its surface area, its IQ, smaller. For the cube, and it's written in a sharp way. Okay, so now we know. So of course, there's a lower bound force for every set. So for every convex body in Rn, you can up to a change of basis, you can bound its surface area, its isoperimetric quotient up to normalization by n, and it's always at least true then by the isoperimetric theorem, and all of this is sharp, and game over, and we understand. This is a very useful theorem. There are times that I use it as a black box in certain places, but it is also an extremely influential theorem, because those of you who know, it is in this context that Keith Ball introduced the geometric form of Brus-complete inequality, and then later that exploded many, many, many applications. So this is a nice use of Brus-complete that you can do this. So this is all very clean. Game over. We understand it very well. And what I want to show, to bring up, is what happens when we allow an additional degree of freedom. Not just choosing the basis of Rn, but also I'm allowing you to perturb the body, but a big O of 1 perturbation, a constant perturbation. So here is the conjecture. I call it isomorphic reverse isoperimetry. So it says the following, that again, so I want to say there exists a universal constant call it C, such that for any subset K over N as before, convex and symmetric, like in Keith Ball's theorem, there exists a change of basis, matrix in SLN, but also end in origin symmetric convex body, call it L inside K, such that so L is a constant approximation of K. So if you multiply L by this universal constant C, it swallows K. Remember, this was contained. L inside S of K is after the change of basis. Okay, so you find inside K this convex body L, but it's a constant approximation of K. You multiply it by 100 or some universal constant. It's a constant approximation of S of K. You multiply it by 100, it swallows it. But for this new body, has isoperimetric quotient, which is just the minimum, the best you can hope for up to constants. So you allow a constant, if you could allow in addition to change of basis, also a constant perturbation, then my conjecture then that you get to the same behavior as the isoperimetric quotient of a Euclidean ball. And that's true for every convex body K in array. Okay, so right, I'm saying you have your K, after applying the transformation, you fatten it up. So this is already S of K. Inside here, you find a smart way to round the corners. This is L. This is a constant approximation. So maybe this is 10 times L or 100 times L. I don't know what the constant will be. But this new L is really like a ball in terms of its surface area. Its isoperimetric quotient is at most root n, not n. You cannot do better than n if you don't allow this perturbation. So we will see later an application of this. I just want to say that, just to full disclosure, for the application, I need a weaker version of this conjecture, which is also open. And so this is a variant of this conjecture, which I would also be happy to solve for the applications. I just need the weak versions of it. So let's go to weak reverse isoperimetry. It's the same thing. So this is constant C as this subset over N. S is the matrix, and L inside K, S of K. Again, convex symmetric, such that, as before, I want this IQ, isoperimetric quotient, to be less than root n, but now I just want it to be not a constant approximation of K, but just to have big volume. So the n, in terms of nth root, so the nth root of L is at least.
There's a question in the audience.
Yeah. Oh, by the way, I should have said that one thing about Zoom is that I never notice questions in the chat. So please say them verbally, because I always.
I have a question.
To the end of the talk. Yeah.
So if I understand correctly, the isoperimetric quotient of L is upper bounded by square root n always?
No, lower bounded. That's isoperimetric quotient. The isoperimetric theorem is that isoperimetric quotient is always at least that of the Euclidean ball. And my conjecture I'm making is that you can always find inside a constant approximation of your body for which the isoperimetric quotient is bounded from above by a different, up to a constant, the best you can hope for, which is root of n.
So I'm saying, like, if you set C in your conjecture to be root n, then this is possible, like, trivially?
Yeah.
You're asking.
Yeah. Then if you set C to be a root n, then you take L to be S of K. And then you use the theorem of Keith-Ball, but not trivially.
Exactly. So I'm saying, like, anything less than C being less than root n is open. Like, is this C being anything less than root n is open?
1 second. Root n you don't need. If you want C to be root n, then it's trivial. It's John's theorem. You can put inside K an ellipsoid, such that if you multiply it by the ellipsoid of maximal volume, so that if you multiply it by root n, it will swallow K. And for an ellipsoid, this is in a fine invariant quantity. It is just equal to the isoperimetric quotient of the ball. So you don't even need to choose. You don't need Keith-Ball's theorem if you want this theorem with the C equals root n. And then you would write here IQ of L is equal to IQ of a ball.
I'm asking, is the conjecture open for anything less than C being root n?
Yeah, but the conjecture is.
Sure.
I have another question. So, if the body
4
is
months old. Yeah. So at the moment, I do not know a bound better than root n, but I did not think very hard about that because I want all or nothing. But yeah, it could be that there is something that you can do better. than root n. I mean, of course, I conjectured you can do a constant, but yeah. So at the moment, off the top of my head, for the purpose of this talk, I do not see a proof that gives better than root n. Okay.
That's another question.
Yeah.
Know that the body is isotropic. Do you need the scaling by S?
Absolutely. Absolutely. So even in Keith-Ball's theorem, where was it? The original one, when you get an n, where did I go? Here. In Keith-Ball's theorem, the S that allows you to reverse the isoperimetric theorem is the S that puts it puts the body in what's called not isotropic position, but minimum surface area position. This means that the surface area measure is isotropic. And you take surface area in the sense that it's a measure on the sphere. You look at the map of the normal, and this maps the boundary of your surface of your body to the sphere. This gives you a measure on the sphere. You want that measure to be isotropic. While isotropic position means that the volumetric are examples showing these two are very different from each other. Okay, so it's not true that the S here is not the isotropic position. It's a different measure. It has to be isotropic, not the volume measure. Is that clear? I don't know. I cannot see, and you're really dots. So I don't know. Yeah. Okay.
I have a really basic question. So for this S, I see how it can be useful to scale the axes. Is there any reason why you would actually rotate the axes, or is that just for convenience?
Yeah. So what if I just took this if I took this rectangle and draw it in diagonal, then you would rotate, right? I could have done this, right?
Yeah. Right, but would that change the surface area to volume ratio? So I see if S changes the scaling, that could help you change the surface area to volume ratio to get something nicer. But does rotation help you at all?
Scaling of what? Okay, when you say scaling, you have to tell me scaling of what?
Oh, okay. So
scaling of the basis, but the basis is not necessarily the standard basis. The right basis when I draw it in diagonal is this direction, is this frame.
Okay. Okay, that helps. Thanks.
Okay. Right. Okay. Okay. So these are the questions, and we will see later that the weak conjecture, suitably formulated, holds up to logarithmic factors. So this is I know this up to logarithmic factors. The strong conjecture, I know it in some cases up to logarithmic factors. In some cases, I know them as stated, but this is just largely open. Before I get to really the real topic of this talk, even though I think that the question is, we can stop here and discuss the question. I'm happy to, but I want to show you some theorems. I want to say I already got a couple questions about this S. So I want to make a convention for the talk.
Ask another question.
Yes.
So in your weaker conjecture, where is C?
Well, it's because I use this notation. I use the twiddle notation, so I didn't. It was redundant.
Okay. Thanks.
Okay. I didn't need to write it this as C because I used the twiddle notation. Okay. So the convention is that all convex bodies, or all convex bodies are unit balls of norms under N that are canonically positioned. what do I mean by canonically positioned? So if you have a norm, X is a normed space, then it has an isometry group. All the linear operators from X to X such that's preserve the norm. Okay, and X is canonically positioned. So X is canonically positioned if there is only one scalar product. On X that is invariant. Under this isometry group. Okay, so in other words, there exists one. Okay, only one. Of course, you can take the scalar product and multiply it by 10. I mean, up to multiplication by a positive constant. There's only one. There's only one identification with Rn which respects the symmetries of the convex body. Okay, and this includes really the questions that I'm going to get to are open for L2 even. Okay, for Rn. So it will be just great to solve all the questions that I'm going to tell you for canonically positioned spaces, but the examples of spaces that you need to think about. So examples are any symmetric norm. So it's when the convex body is invariant under permutations of the coordinates and changing and flipping along any of the axes. Symmetric norms, and if you want Schatten classes. So I'm really interested in matrices. So we look any norm on M and R and the n by n matrices, which is invariant under permutations of rows. You can just permute rows, permute columns, or change a sign. Just take one of the rows or one of the columns and change it to minus of itself, of the entire row. So really all the operator norms that you know, operator norms from LP to LQ, those of you know tensor products, projective, injective tensor products, Schatten classes, unitary ideals, all of these norms which we really, really need, right? The nuclear norm, Schatten 1, all of those are canonically positioned. And for all of those, you do not need to discuss this S. There's really a unique S. So the conjecture in this case, symmetrical version, okay, you want to call it symmetric. Reverse isoperimetry. Then I don't have this S, and I won't forget. Then I won't forget it. It says that so for every K which is canonically positioned, there exists an L inside K, such that IQ of L is less than root n, and the volume of L is at least the volume of K, the nth root. Okay, so is the notion of canonical position clear? And this is really for the simplification of the talk, but it's really the classes of spaces that we care about. I'm going to get to questions that it's even open for Hilbert space, for Rn L2 of dimension n. So this is really not, I mean, I do care about the questions about general norms. If you go to the paper, which is online, it deals with general norms, it tells how to change everything, but that's kind of a luxury for the future to solve it for general norms. So canonically includes all the matrix norms that we know of, that we use a lot in computer science and in geometry. Anything that has, as I said, any normal matrices which is under permutations of rows and columns separately, and flipping sign of an entire row or an entire column. So we can think of those for now. Is that clear? And then I don't have this S, and I won't forget it because I don't need it anymore. Is this clear for everybody, or this assumption? For the sake of the talk. Okay. So this was this was a conjecture. Yes. Yes.
Yeah. Somehow your sound is breaking up a little bit.
Yeah. Is this better?
Yeah.
Yeah, and I realize what's happening is sometimes I move my iPad and it becomes flush with my laptop. I'm moving, and I guess it blocks the microphone. Okay, is this good?
Now it's much better. Yeah.
Yeah. Okay. Good. So it's actually a physical thing in my attic where you are. Okay. 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 So I want to discuss. There are two invariants of metric spaces. One of them is related to extension of Lipschitz functions. The other one is related to clustering. Because of the venue here, I'm going to focus on the clustering, which is an old question, but not as old as the application that I'm going to show you later to extensions of Lipschitz functions. So here's just the definition, which is due to Bartal. So if you have a metric space, let's say M with some metric, a metric space, and then I just say assign to it a number called the separation modulus. Of M, denoted sep M, is the smallest sigma. I'm guessing that most people in the audience seen this before, such that for every delta bigger than 0, there is a random partition of M into clusters diameter at most delta, such that if you give me any 2 points in M, you look at the probability that X and Y belong to different clusters. That's less than the sigma times the distance from X to Y and make it scale invariant. So I divide by the scale that we're dealing with. Okay, so this is this number that you associate to every metric space, sep of M, the separation modulus, is invariant under by Lipschitz transformations, or and it's an embedding, and it's a very, I guess, the most basic notion of random partition, of which some sort of stochastically boundaries are small. Near points with that are nearby fall into the same set with high probability. So here's the theorem. In 2021, it's December, almost this year. It's already in the archive. And it says the following, that, so I'll write it in a conditional way first. So let X, which is our N with some norm, I'll say it in words, even though I said this is the assumption for the rest of the talk, be a canonically positioned space. So if isomorphic, weak isomorphic, I need just the weak version, reverse isoperimetry. Holds for X, then I can compute this. Even so, this parameter sep of X is Rn with some norm. I'm allowing you any distribution over partitions, any shapes, just with the bounds and the diameter. Seems like a very nonlinear invariant, yet it's bounded above and below by universal constants times the following. I'll write this called the volume ratio of the dual of X times root of the dimension. Let me just define it. So volume of X is, I need the dual, but the volume ratio of X It's called the volume ratio of X. It's an extremely well-studied parameter. There is tons of literature on it. And it's the following. So you take X, it's for any norm. You take, you look at the unit, you like Bx is the unit ball. And then you look at, let epsilon be the ellipsoid of maximal volume. In X, inside X. Inside B of X, sorry. And then the volume ratio is just, you look at the volume of the ball divided by the volume of epsilon, just takes the nth root. So look at the best approximation after nth roots in sense of volume, in the sense of volume of the unit ball of X by an ellipsoid. Okay? So this is what the volume ratio of X is. And then if we go, so this is just really computing volumes. And what the theorem says that if you could reverse the isoperimetric theorem, as I said, then you just have a formula. This thing which seems like a non-linear complicated. Just computing the volume ratio of the dual dimension. What?
Your audio is breaking up.
Yes, now I can. But I think now it's on your side because I can't hear you. Can you hear me better?
Now we can hear you.
You can or you can't?
Can. So it's good.
Okay. I'm guessing that this was on your side because I also couldn't hear you for a moment. Okay, so this is some sort of a formula which relates linear to nonlinear. So the minute you have this at hand, there is so much literature that computes these volume ratios. In many cases, it's so well studied that you just have formulas for the separation modulus. Okay, I'll give you some examples later. So this is a theorem, it's conditional on solving the reverse isoperimetric problem. Here's a theorem which is not conditional, which is because reverse isoperimetry holds up to logarithm. So this is really a theorem without any assumption, which is as above step of X. If you don't care about lower order factors, then you know it. Is volume ratio times n to the half plus little of 1. The little of 1 is a log. Okay, so if you want to know the answer up to lower order factors, then we just solve the problem. Okay. So you start with arbitrary partitions, and you end up with just computing the volume of the ellipsoid, the volume of the unit ball, and the volume of the biggest ellipsoid inside the body. So you can get from this many free things. Let me just take one example, just so you see. So, like example of a canonically positioned space that you might care about. What's going on here? So, for example, you can take X to be. So I want to know what is the separation modulus. So again, up to lower order factors. The separation modulus of, let's say, n by n matrices. And the norm that I take is the operator norm from LPn to LQn. So I take a matrix n by n, I think of it as an operator from LP to LQ. That's a perfectly legitimate norm. It is invariant under, as I said, permutations of rows, columns, changing a sign of a row, sign of a column. It's canonically positioned. Plug it into this theorem, crunch the numbers, and you get the following answer. And it's a formula. I mean, it looks crazy, but it's the truth. It's really the same as so if P and Q are at least 2, both of them, then the answer is n to the 3/2 minus 1 over the smaller, the minimum of P and Q. If they're both less than 2, P and Q, then you get n to the 1/2 plus 1 over their max. If P and Q are on two sides of 2, but in this way, that P is less than 2 and Q is bigger than 2, then the answer is n. And if it's the other way around, they straddle 2 by putting Q less than 2 and P more than 2, then you get n, and then you get another change of behavior. There is the maximum of two numbers, 1 and 1 over q minus 1 over p plus a half. So when this hits a half, you get different asymptotics. And this is the best way to partition randomly n by n matrices with the operator norm from LP to LQ. And this just comes from using this theorem and then computing the volumes. And this is in the literature. You just go to the 1980s. People have been studying volume ratios left and right, and you find the relevant references. Okay. And I just chose one. It looks complicated, but this is the answer. Okay. So these are the kind of things you can do when you because the volumes, these are lots of very, very low hanging fruits the minute you relate these to volumes. Before I'm going to get to Lipschitz extension, and I want to just say that I formulated everything here by the separation modulus of the entire space. So a norm and our n, but I look at all of our n. But we all care about this method. I don't have this method allows you to compute things for subsets. So, so for example, let me find it. So those of you know, so you can look at, so take P and NP, and you look at SPN. This is n by n matrices, n by n matrices with Schatten P norm. Right, so it's the norm of a matrix A is just the LP norm with singular values. If you want the trace of A star, P over 2, then all of this 1 over P. And then you can look inside it. So you can look, so for every R less than N, you can look at SPN less or equal to R. I guess this is matrices of rank at most R in SPN. So this is a natural object, and then the formula, and then you can get a formula for this subset. So I'll tell you what it is in a second. It is so the theorem that you get from this. It's not from the theorem I said it above because I did it for the whole space, but in the paper you can see how you deal with subsets as well. So you get the SEP of SPN less or equal to R is just, again, up to lower order factors. It is, we have this root of n, and then you multiply it by the bigger of root of the rank, and the rank to the 1 over P. This is, again, so you can handle things of this type. So if you care about low rank matrices, then you know the best way to partition them randomly in this sense. So this is, and there are more statements you can read in the paper, other norms, and I computed those volumes. Like, these were low-hanging fruits. The minute you have the volumes computations, and you can look at the literature. So these are just examples. What I want to do next is I want to show you my original motivation, which is connection to Lipschitz extension, and then I want to say a word or two about the proofs. Yeah.
Is it easy to see what the random partitions are? Or like,
you want me to skip the proof? Okay, you know what? Okay, so what you're asking me is what I was planning to do in the end. Let me do it now. Okay. So there is really a canonical. If you have a metric space, M, D, and you have also a probability measure. Mu is a probability measure on M. then there is a standard way, it's what's called iterative ball partitioning. That's what everybody uses and what I use as well. And which is the following: take IID points, select IID points according to you. So x1, x2, x3, etc. are IID samples from you. Okay. And we wanted to shoot for some diameter. So there's some delta bigger than 0. That's the bound of the diameter that I'm going to get for the partition. Okay. And then what I'm going to say is so the first cluster, so C1, if you want, of the random partition is just the ball around this random point x1 of radius delta over 2 to make it diameter 1. And C2 is going to be the ball around x2 of delta over 2 minus the previous ball. And C3 is going to be the ball around x3 of the delta over 2 minus the union of the previous balls. It's the obvious thing that you want to do is that you have these random points. So x1 shows up, it bites out a ball radius delta out of the space. Here is x2, it's x1, etc. x3. Eventually, maybe you chose like this, eventually a point shows up here and then it takes what it can out of the space. And this, of course, as you go along in this structure, in this construction, eventually the sets become really nasty. They don't have to be connected. They can be like a little fragment here, a little fragment here. But every point tries to bite out of the space a ball of radius through delta over 2. A ball of radius delta over 2 of what remains, those that have been taken before. So that's iterative ball partitioning. That is really the most standard thing that you can do and very natural. So the construction, and this is really the observation that led to all of this, is that it pays off to actually first solve the reverse isoperimetric problem before doing this. Say the unit ball of my space, of my norm was this. Let's solve the weak reverse isoperimetric problem, find this L inside, which has smaller isoperimetric quotient, so that was Bx. Solve this, and then draw this picture not in using balls in the intrinsic geometry of X, is just a constant factor approximation of the original one. So it will just influence constants, but it changes everything when you start analyzing this. Okay, so the isoperimetric quotient comes in when you analyze what this does, and you just see that what you want is to solve the problem, this reverse isoperimetric problem.
Yeah, we can hear you again.
And then there are screens. Really? And now? So can you hear me?
Now we can.
Can you hear me? I have no idea what's going on. So what was the last word that you heard? What was the last thing I said? When did you stop? I just, okay, nobody wants to say. So I'm doing the usual iterative ball partitioning with random balls, except that you choose shapes which are not balls, and they are a solution of the reverse isoperimetric problem for the given metric space. And this additional degree of freedom, obvious in hindsight, gives you the partition. And then you have to prove that you cannot do better than that. And that's some sort of isoperimetric type argument using Loomis-Whitney. Is that okay? So that was and there are computations to do, but really that's the role of the reverse isoperimetric problem is to change these circles here to the right shape that you're going to be biting out of the space. Is that clear?
Yeah.
Oh, okay. So So first of all, I think it's interesting to just compute the invariant set for metric spaces, and at least for canonically position metric spaces, we know what to do, right? So again, you need to solve the reverse isoperimetric problem. In many cases, I wrote solutions in the paper. In some cases, I don't know, but anyways, I know it up to logarithms. So up to lower order factors, we know the answer, and the answer is just compute volumes. Okay. However, there is a much older question where there is extremely tantalizing open questions, which extremely frustrating. I think many people for many decades have been working on them, and there is very basic things are open. So I want to tell you about those. And this led to some progress in which is satisfactory in like one little corner of this big universe. So it's called the Lipschitz extension problem. And the setting is you have a metric space M. And so this is just a metric space. And I'm going to define E of M. This is what's called the Lipschitz extension modulus. And that is the smallest k, the inf over k, such that, and now I'm going to have lots of quantifiers. So for every subset A of M, for every Banach space, see, for every one Lipschitz function, defining the subset, going into Z, there exists F tilde defined on all of M, going into the same Z, which is extends F such that F tilde extends F, it coincides with F on the subset A, and the Lipschitz constant of F, so tilde, I mean, is at most is K. The initial was one Lipschitz, and you want to extend it in such a way to the function K Lipschitz, the smallest K, such that you can do it for every possible subset and for every possible target space, is called the Lipschitz extension modulus of M. EM, where is it? EM. Okay, is the definition clear? So this is bounding EM. This is really a workhorse in many of analysis. It's used. Probably for me, maybe for many of you, every other paper at least that I write has a lemma where I extend some Lipschitz function at some point. And so knowing bounds and these things is very useful. It's sometimes there are surprising applications of it, but a lot of the times there are just obvious applications where you have some partially defined function and some subset. You want to analyze it using continuous methods, compute its Fourier transform, differentiate it, apply heat flow to it, things of this type, but it's defined in a subset. So you want to extend it in a nice way so that you can use analysis to analyze it. That's the banal way to use these things. There are also surprising applications of Lipschitz extension, but this is really a workhorse of analysis in geometry. And I know that there are many people in the audience. I don't need to tell you this, but if you have questions of examples, you're going to open Pandora's box, but we can start talking about it. I'll be happy to answer. So this is a Lipschitz extension modulus. There's a huge amount of literature of this. On this, many great ideas were invented to study it. Those of you who know, the Johnson-Lindeshelf's lemma came from this. Markov type came from this. There are many very nice ideas that go into this literature. But the theorem that, in the case of norm spaces, the last progress was in 1986. This is a famous theorem of Johnson, Lindenstrauss, Shechtman, 1986, which says that if X is an n-dimensional norm space, then E of X is a constant multiple of the dimension. Those of you who know this, there is something called the Whitney extension problem, or Whitney's extension method, Whitney cubes, Calderon-Zygmund decompositions. They use the Whitney's extension method here, but in a way with a nice, very nice, clever twist that I haven't seen used before. So there's some very nice contribution in this paper to an old method. So if you have an n-dimensional space, you can always extend the, let's say, a one Lipschitz function by a subset going into anywhere, any Banach space. Then we don't need the target to be a Banach space. We know it can be a non-positively curved manifold. A lot of these things are understood. They just simplify things. Suppose it's a Banach space. So you have a one Lipschitz function, an arbitrary subset of this normed space. Then you can extend and you lose a function of, and then the extended function is n Lipschitz. So just to see how, so this 1986, great open question is, I have no idea, can this be improved? So can you get this to little open? I have no idea, an absolutely wonderful open question about n-dimensional normed spaces. So up to the theorem that I'm going to tell you now, which is December last year. So this was, so up to the theorem, so a question, compute E of n up to constant factors. Oh, not M, E of X, sorry, E of X. X is again an n-dimensional normed space. For any normed space. It's really a sequence of norm spaces going to infinity. Really not a single sequence of norm spaces was this computed for. So in particular, here's a great open question. What is growth rate of E of Rn with the Euclidean metric? And the best known bounds are that E of L to N are at most root n and at least fourth root of n. Okay, but we do not know the asymptotics about Hilbert. The question about Rn. Oh, I should have said that when I defined this Lipschitz extension modulus here, the way I defined it, I had this quantifier for every subset, for every target Banach space Z, for every function f. Because the quantifiers are like that, you can apply a very simple duality argument, and you can understand what this is in terms of the intrinsic geometry of M without ever referring to a target Banach space or Lipschitz function. This is something about, it's a geometric question about M itself. I'm not stating it right now, but if I'm asked later, I can tell you what it is. It's sometimes a useful perspective. But this is this question that I'm asking, what is E of L to N? I can state it as a question about Rn with Euclidean norm. I'm not mentioning any Lipschitz function anywhere, not mentioning any arbitrary target Banach space, about Rn, the usual Rn, the room you sit in, except the high dimensional version of it. Okay? Now just so to tell you what the enemy is, it's that this wasn't completely clear what are we shooting for if you want to understand this up to lower order factors. So here's a theorem in the same paper. It says that E of X is at least n to the C for any n-dimensional X. Normed space. X. C is a universal constant. So there's an upper bound of n, there's a lower bound of n to the c. So if you want to know this, to answer this question here, the game is what is the power of n. Just this is before this we knew lower bound going to infinity, which was going slower than any power, like e to the root log n. This is again has a history which I will not get into. But the answer is at least n to a power. So the game is what is the power of n. That's the interesting invariance. Just like in there were these funny powers when I wrote to you the separation modulus of the matrices with operator norm from LP to LQ. The game is what is the power of the dimension in the extension problem. Okay, so the point is this is for any norm space. For L2, it's written here. So here's a theorem that follows from the L infinity version. In the same paper, it's all online, that E of L infinity n is root n up to universal constants. And actually that's, so before I wrote this paper, there were 0 examples of spaces for which we know their Lipschitz extension modulus. And now there's only one, because the proof gives an upper bound, which is better than the best known upper bound for many, many spaces, but it matches the lower bound only for L infinity n and for spaces that I can go over the proof and artificially give you spaces for which it's sharp, but none of the really natural spaces. So we have only one example, and I don't know the answer for L4, L2, L1, etc. I don't know. So for L infinity, the answer is root n, but this is the only example I can give right now. And this is where the bounds matched. And in L infinity n is exactly where, I should have said so there are in all of these things there are two sides, right? There is a lower bound and an upper bound. A lower bound is to find a way to show that you have to cook up some function which is one Lipschitz, but it's not a restriction of any function which is a small Lipschitz constant. So that usually involves some invariance to compute. So there's a lower bound. In the separation modulus lower bound, you have to prove that it's impossible to partition space in a certain way. And then there's the upper bound. The upper bound, for Lipschitz extension, there are many ways to prove it, but the upper bound is a theorem. There's a theorem that Lee and I proved back in 2005, 2004, which is that E of M is always less than SEP. Okay, so I'm using the previous theorem. So it's a random partition. So it's a random version of this Whitney multi-scale partition method that people have been using forever. When you add randomization, then you get this bound, and then I can prove use the previous theorem. So for SEP of L infinity n is root n. And over there again, so right, L infinity n, its unit ball is a cube, right? And they pack space perfectly. They're a perfect packing of space. But when you do this randomization, right, this random construction, if you draw a cube around every random point, and you do the computation, you will get n, the bound of Johnson, Schwarz, and Shefman. You won't get anything better. However, if you solve the reverse isoperimetric problem for the cube, so you take your cube, and it's going to be, and you solve the problem for the cube, and I give an approximate solution in the paper. You round the corners in a smart way, and then use this rounded cube with rounded corners in order to do the random partition. It seems not wise, because now this new shape does not pack our n, but it's better for this construction, and it takes the n down to root of n, which is sharp. So that's one of the applications of this. Okay, I'm a minute over time, so I'll stop. But I'm happy to answer questions.